We've all been there, right? You're stuck on a problem, and the instinct is, well, just keep pushing. Spend more time, dig deeper.
Yeah, more effort. It usually feels like the way to get a better solution.
Exactly. But what if that same instinct, that feeling, is actually kind of misleading when we're talking about how artificial intelligence thinks?
That's really the fascinating question we're diving into today. We're looking at some pretty surprising new research that makes you reconsider how we approach AI reasoning.
And for you, the learner, welcome back to the deep dive. Our whole goal here is simple. Get you a solid grasp of this important topic, quickly and thoroughly without making your head spin.
Exactly. Think of it as your fast track.
Yeah, your fast track to understanding some genuinely surprising stuff happening in AI right now.
So we're focusing on this specific study. It's called Don't Overthink It, Preferring Shorter Thinking Chains for Improved LLM Reasoning. And this paper looks at how these large language models, LLMs, the really powerful AI behind a lot of cutting-edge tech, how they tackle complex problems, particularly math problems.
Right, and the big surprise, the thing that really, jumped out at me is this finding. Sometimes when an AI is trying to solve something, using less internal thinking, fewer steps in its reasoning process, it actually leads to more accurate answers. It just feels completely backwards, doesn't it?
It absolutely does. Because, for a long time, the sort of accepted wisdom in the field, it's been that to get the best performance out of these reasoning LLMs on tough tasks.
You needed more compute.
Exactly. You needed to scale up the computation time during testing. The whole idea was generating these long, really detailed sequences of thought, step-by-step reasoning. That was supposed to lead to more correct answers.
Okay.
And there was even some earlier work that seemed to back that up, suggesting longer AI responses showed better reasoning.
Okay, let's unpack that a bit. So the standard thinking was kind of like showing all your work in a math problem, but like amplified for an AI.
That's a good way to put it, yeah.
The AI generates this long chain of internal thoughts before spitting out the final answer. And everyone just assumed, well, the more detailed that chain, the better the final answer must be.
Precisely. But the researchers behind this new study, they started to question that basic assumption. They asked this really critical question. Does generating more and more of these thinking steps, which we measure as more tokens, basically units of processing,
Right.
does that inevitably lead to better performance in an LLM? Is longer always better when it comes to AI reasoning?
And this is where it gets really interesting, isn't it? They took, 3 of the leading reasoning LLMs?
Yep, some of the smartest models out there.
And had them work on some seriously difficult math problems. But crucially, they didn't just get one answer. They had each AI generate multiple different answers for the exact same problem.
Exactly. And what they found was, it was pretty remarkable. They noticed that among all the different reasoning paths the AI took to solve a single math problem, the shorter paths were significantly more likely to end up at the correct answer.
Significantly. Like how much more likely?
Get this, they quantified it. For the same question, the shortest reasoning paths were up to a staggering 34.5% more accurate than the longest paths generated by the very same AI model.
Wow. 34.5%.
Yeah.
That's not noise. That's a huge advantage for the quicker reasoning.
It's massive.
Okay, to really help us get a handle on this, the paper included an example, right?
Yeah.
Figure 1. Can you walk us through that?
Absolutely. Yeah, figure 1 illustrates it really well. So imagine a math problem. The LLM tries to solve it multiple times, right?
Right.
And in these different attempts, it comes up with various internal thinking chains that lead to final answers of, say, 52, 33, another 52, and 49.
Got it. Different paths, different answers sometimes.
Exactly. Now, the standard method, which is called majority voting, would just look at those final answers, 52, 33, 52, 49, and pick the one that shows up most often.
So 52 in this case.
Right, 52. And typically, the system would have waited until all the thinking processes, including the longest, most drawn-out one, were totally finished.
Okay, so wait for everyone to finish thinking, then count the votes. Makes sense, intuitively.
It does. But the researchers proposed this new method. They call it short M at K.
Short M at K.
Yeah. And in their example, using a specific version called short 1 at K, the system does something different. It stops all the processing as soon as the shortest thinking process is complete.
Ah, okay.
So in this particular run, the shortest think led to the answer 49. So instead of waiting around for those longer reasonings that gave 52 and 33, they just stopped early and got 49.
And crucially, 49 might actually be the correct answer, even though it wasn't the most frequent one the AI came up with overall.
Precisely.
So the idea is don't let the AI overthink it. Go with the quicker insight. It's almost like trusting its gut feeling, if AI had guts, you know?
Yeah. Huh. Exactly. And this observation led them to formalize their short M at K inference method. The basic idea is run multiple attempts at the problem in parallel.
Okay, like brainstorming.
Kind of, but here's the key difference. You don't wait for all of them to finish. Instead, you stop the computation once the first thinking processes are done, being some number you choose, like 1 or 3.
Right.
The final answer is then chosen by a majority vote among just those shortest, fastest reasoning paths.
And if there's a tie among those?
Good question. If there's a tie, you break it by selecting the answer that came from the absolute shortest reasoning chain among the tied ones.
So you're prioritizing speed and conciseness throughout the process. Instead of waiting for the slowpokes, you bet on the AI's quick wit.
Exactly. It's like taking the first few good ideas from that brainstorming session, which are often the best anyway.
Right. So it seems like a speed round for AI problem solving. Get a few quick takes, go with the consensus among the faster ones. What are the big advantages here? It sounds like it could save a lot of processing power.
You're absolutely right. The efficiency gains are really significant. Let's take short 1 at K, where you just use the answer from the single shortest path.
Okay.
The researchers found this method could get similar or sometimes even better performance than standard majority voting, but, and this is key, while using up to 40% fewer thinking tokens.
40%? Wow.
Yeah, especially when computing resources are a bit tight. That's a huge saving in computational costs. 40% less compute is.
Well, it's like getting the same brain power for a much smaller electricity bill.
That's a massive saving, seriously.
And it gets even more interesting. They also looked at short 3 at K, where they wait for the first 3 shortest paths to finish.
Right, taking a quick consensus.
Yes, and that method consistently outperformed the standard majority voting across all the different levels of computing power they tested. And it could be up to 33% faster in terms of the actual time it takes to get the answer.
Okay, so hold on. Potentially more accurate, significantly faster, and cheaper to run. This really sounds like a potential breakthrough if it holds up.
It seems that way. How did they actually test it? What kinds of math problems and which AI models did they use?
So they used 3 pretty well-known leading reasoning LLMs, LN Super 49B, R132B, and QWQ32B. These are all very capable models.
Okay.
And to evaluate them, they used 3 highly competitive math benchmarks. Think like really tough exam questions derived from actual math competitions. AIM 2024, AIM 2025, and HMMT February 2025.
So serious math challenges.
Definitely. They cover a wide range of topics, different difficulty levels, and for each question on these benchmarks, they generated 20 different responses from each model.
20 tries per question. Okay, that gives a good sample size.
Exactly, a good sample of their different reason approaches.
So they put these top AI brains through a rigorous math test, analyzed all their different attempts. What did they find about how the difficulty of the question affected how long the AI thought?
That's a really insightful question. And their findings, which they summarized in Table 1, did confirm something others have seen too. The models tend to use more tokens, more processing steps when they're tackling harder questions.
Makes sense.
Yeah, in some cases, the reasoning was up to 2.9 times longer for the really challenging problems, which, might initially lead you back to thinking, okay, harder problems just need more thinking.
Right, it seems logical. The tougher the puzzle, the more steps you'd expect are needed to figure it out.
Exactly. But, and here's the crucial twist. Within each individual question, regardless of how hard it was overall, the correct answers consistently came from shorter reasoning paths compared to the incorrect ones.
Ah, okay. So even when the AI took a longer, more winding road, it was actually more likely to end up at the wrong place.
That's what the data shows. The quicker, more direct routes were more often the right ones. It's really counterintuitive.
It really is. And Table 2 in the paper digs into this comparison more directly, right? Short versus long thinking chains for the exact same question.
Yes, that table has some really striking data. They compared the shortest thinking path, the longest one, and a randomly selected one for each question attempt.
And what did that show?
Well, first, the shortest answers were, unsurprisingly, much shorter, like 25% to 50% shorter than the random ones. But more importantly, just picking the answer that came from the shortest thinking path actually boosted performance.
Boosted at how much?
By an average of 2.2% up to 15.7% across the different benchmarks, compared to just picking an answer from a random path.
Okay, that's a solid gain just by favoring brevity.
Right.
But what about the long thinking paths? Surely they must have been more accurate given that old assumption.
Nope. Quite the opposite, actually. The longest thinking paths used way more tokens, up to 75% more sometimes.
No.
And they saw a significant drop in performance. Accuracy went down by 12% to 18.8% on average, compared to just picking a random answer.
So wait, the absolute difference in accuracy between just taking the shortest answer versus the longest one.
It could be as high as a 34.5% increase in average accuracy for the shortest path, all while using way fewer thinking tokens.
So the AI was essentially overthinking itself into making more mistakes. The longer it chewed on the problem, the more likely it was to get it wrong.
It certainly looks that way.
This really does turn that old idea,
Yeah.
more compute equals better reasoning, on its head.
Absolutely. And this core observation, this pattern, became the foundation for their short M at K inference method.
Right.
Now, they didn't just stop at noticing this trend. They went on to rigorously test short M at K against the standard majority voting method. They looked at different factors, like the number of samples generated, that's the K, in their short M at K notation.
Okay, how many attempts the AI makes.
Right. And also the total amount of thinking compute used, and critically, the actual time it took to get an answer. These results are laid out really nicely in figures 2, 3, and 4 in the paper.
Okay, let's dig into those figures then. What were the main takeaways when they compared these different ways of getting the final answer?
Okay, so figure 2 shows something you might expect. Generally, all the methods get better, more accurate as you generate more samples, so as K gets bigger, more tries usually help. But what's fascinating is that this holds true for their short M at K methods too. Even with more attempts, the shorter thinking paths among them are still more likely to be the right ones.
Interesting.
And when they directly compared short 1 at K, just taking the single shortest to majority voting, they found short 1 at K actually did better than majority voting when they used fewer samples overall.
So less weighting, potentially better result with fewer tries.
Yes, and particularly in situations with limited computing power. For one of the models, LN Super 49B, short 1 at K, matched or even beat majority voting across all compute budgets.
That's impressive. So even with fewer overall tries, using the short 1 at K approach could outperform the standard method that waits for all the longer processes to finish.
Exactly. And then there's short 3 at K, where they take that quick majority vote among the first 3 shortest paths.
Right.
That one consistently achieved higher performance than standard majority voting while using less total thinking compute. Figure 3 really highlights this across the board. Short 3 at K generally came out on top in terms of accuracy for a given compute budget.
Okay. Better accuracy, less compute. What about speed? Actual time to get the answer. That's figure 4, right?
Yes, and this is another key advantage for short M at K. See, with standard majority voting, the time it takes usually goes up as you generate more samples because you always have to wait for the slowest, longest reasoning path to finish.
Makes sense. You're limited by the slowest one.
Right. But with the short M at K methods, they can actually get faster as you increase the number of samples K.
Faster with more samples? How does that work?
Because the more attempts you run in parallel, the higher the probability that one of them will finish really quickly with a short path. And since you stop as soon as you have your M shortest paths, a larger K increases the chance of hitting that stopping condition sooner.
Ah, I see. More runners means a higher chance one finishes fast.
Exactly. They found short 3 at K, for instance, could be significantly faster than majority voting, while also giving better performance.
So let me summarize. Potentially better answer uses less computational power, and you get it faster. That feels like, well, a trifecta of advantages.
It really does look that way based on the results.
They also did some finer-grained analysis, right? Ablation studies, to really pick apart the short M at K method itself.
They did, yeah. Figure 5a looked at the value of how many shortest paths you wait for. They found short 1 at K is really good when compute is scarce. Using slightly larger M values, like 3, performed comparably well and maybe slightly better when more compute was available.
Okay, so there's a slight trade-off there depending on resource.
A little bit. And Figure 5b looked at how to break ties. Remember, if the first M paths give you, say, 2 votes for answer A and 2 for answer B.
Right. How do you choose?
They tested different tie-breaking rules. And they found that choosing the answer that came from the absolute shortest reasoning path among those tied options was the best strategy, better than picking randomly, and definitely better than picking the one from the longest path among the tied ones.
So even in a tie among the quick thinkers, the very fastest one is still the best bet. It keeps reinforcing that core idea.
Exactly. It's remarkably consistent.
This is really fascinating stuff. Now, they didn't just stop at observing this and creating a new method. They also look into whether you could actually train the AI models themselves to prefer shorter reasoning. True fine-tuning.
Yes, exactly. That's covered in Section 5. They took one of their best models, QWQ-R32B, and used it to create 3 different training datasets based on its own problem-solving attempts.
How did they make the data sets different?
So for a bunch of questions, they generated multiple answers. Then they made one dataset, S1 short, using only examples where the AI used its shortest reasoning paths. Another dataset, S1 long, used the longest paths. And a third, S1 random, used randomly selected paths as a baseline.
Okay, short, long, and random reasoning examples.
Right. Then they took another powerful model, Quen 2.532b, and fine-tuned separate versions of it on each of these datasets. The results are in Table 3.
And what did they find? Did training the AI on examples of short, effective reasoning actually make it, well, reason more concisely and better?
It seems so. The model that was fine-tuned specifically on the S1 short dataset showed improved performance on the math benchmarks compared to the one trained on the random examples.
An improvement in accuracy.
Yes, about a 2.8% relative improvement. And interestingly, it achieved this while also using fewer thinking tokens on average, about 5.8% less.
So it got smarter and more efficient just by learning from concise examples.
Pretty much. On the flip side, fine-tuning on the S1 long dataset, the examples of long reasoning, didn't really give any significant performance boost. And maybe not surprisingly, that model ended up using more tokens in its thinking.
So showing the AI examples of effective short reasoning actually guided it towards thinking more efficiently and accurately itself. That seems like a really powerful implication for how we might develop these models going forward.
It really is. It suggests we could potentially build more efficient models from the ground up by emphasizing this kind of concise reasoning during training.
Now, did the researchers mention any downsides or limitations to their short MK method?
They did point out one main limitation. The method, especially the efficiency gains, works best when the AI can run those multiple attempts of the K different thinking paths at the same time in parallel.
Which requires certain hardware or setup, right?
Right. It relies on what's called batch decoding. That might not always be feasible, especially if you have very limited memory resources. However, they do note you could still use the core idea sequentially, try one path, then another, stopping early, but some of the speed benefits would be reduced. It'd be like one person trying different approaches, one after another, instead of a team working together.
Okay, so it's most efficient with parallel processing. And looking at the bigger picture here, what's the potential impact of this research beyond just making AI better or faster at math problems?
Well, the broader impact could be quite significant. This work points towards a way to make these powerful reasoning LLMs more efficient and therefore more accessible. By potentially reducing the computational costs and the time needed to get good answers, these advanced AI tools could become more widely available. Think about running them on less powerful hardware or making them cheaper to operate at scale. It could open up advanced AI reasoning to more users and many more applications.
Okay, let's try and wrap this up. For you, the learner, what's the absolute key takeaway message here?
I think the core message is this, that long-held belief that more thinking time or more complex reasoning steps by an AI always leads to better answers on hard problems. Well, it just isn't necessarily true.
Right.
In fact, this research strongly suggests that longer thinking can often lead to worse results. Shorter, more concise reasoning paths can actually be more effective and much more computationally efficient.
So it's a potential shift in how we think about AI intelligence.
Yeah.
Speed and conciseness might actually be markers of effective reasoning, not a lack of depth.
Exactly. So next time we think about AI tackling a tough problem, we shouldn't automatically assume the one churning away for the longest time is the smartest one in the room. It might just be, well, overthinking it.
And practically, this short MK method seems like a really promising tool.
Yeah.
It offers a way to potentially get faster and more accurate answers from these LLMs using less energy, less compute.
Right. And that idea of fine-tuning models specifically on shorter, effective reasoning paths could lead to a new generation of AI that's inherently more efficient and maybe even more capable.
Absolutely. Which leads us to a final thought for you to maybe chew on.
What are the wider implications here? If shorter thinking can be better for AI, what does that mean for how we design them, how we interact with them in the future?
Yeah. And does it maybe even change how we think about intelligence or problem solving more broadly, even perhaps in ourselves?
Exactly. Are there times when our own tendency to overthink things actually gets in the way of finding the best, simplest solution? It's definitely something worth reflecting on.